In this video, we're going to look at formally proving a limit. So how do we go about proving that the limit of a function actually is a value? Not just by guessing, not by looking at a graph or looking at it numerically, plugging in values and just saying, oh, it looks like it's getting close. But how do we actually do that formally? Now, we use our formal definition. It says for the limit as x approaches c of f of x is equal to L means for every epsilon greater than 0, there's a delta larger than 0, such that if our value of x is within delta units of c, then our function value f of x should be within epsilon units of L. And so here we want to show the limit as x approaches 1 of this function is equal to 0. So our value of c in this problem is 1, our limit L is 0, and our function f of x is x squared minus 2x plus 1 over x minus 1. So we're going to try to prove that. Now to prove this, really what we need to do is we need to figure out what choice of delta do we need to make in order to make our f of x minus L be less than epsilon, regardless of what epsilon we choose. So we have some scratch work that we will do. It's not part of the formal proof, but it's stuff that we do over to the side. So we found our function. We are going to start with this right here. The f of x minus L is less than epsilon. Our function f of x is x squared minus 2x plus 1 over x minus 1. Minus L, our value of L was 0, is less than epsilon. We're going to leave that as epsilon itself. We want to go through a series of steps and end up with the absolute value of x minus c. In our case, c is equal to 1 is less than delta. And so whatever value you have here, that is going to be your value of delta. All right, so let's do some work. So if we take x squared minus 2x plus 1 over x minus 1, we could factor the top into x plus 1 times x minus 1. Nope, we can't factor the top in that way. It's x minus 1 times x minus 1. Over x minus 1. One of those x minus 1s will cancel. So we have x minus 1 is less than epsilon. And so here, this left-hand side is exactly what we're targeting. And so we are going to choose delta to be equal to epsilon. All right, so that's not the proof. That's just the work, the observation we need to make kind of in the background before we do the proof. All right, and so here's our proof. Given any epsilon greater than 0, let delta be equal to epsilon. Now, why are we letting delta be equal to epsilon? Well, because we did that scratch work over to the side, or we did that scratch work in the background. In math textbooks later on, or math papers later on in your life that you might encounter, all of the scratch work is left as an exercise for the reader, and so you would just have to do that on your own. It feels like the delta is just magically showing up. It's not magically showing up. The author of those texts has done scratch work just like this in the background at some point in time. All right, so given any epsilon greater than 0, let delta be equal to epsilon. Then if we have the absolute value 0 less than the absolute value of x minus 1 less than delta, which is equal to epsilon, then absolute value of x minus 1 is less than epsilon, which implies that the absolute value of x minus 1 times x minus 1 over x minus 1 minus 0 is less than epsilon. So x squared minus 2x plus 1 over x minus 1 minus 0 is less than epsilon. And that's it. Right? We have proven what we wanted. Right? We needed to show that if this was true, then this was true. No matter what value of epsilon you choose, you can find an appropriate delta that will make that stuff that I highlighted in blue be equal. That is our formal proof. We will look at another example of this in our next video. I will see you there.